Dear students, in last class we have studied DIF FFT algorithm to find n-point DFT. Today we will solve two problems on finding the DFT and IDFT using DIF FFT algorithm. First one, using DIF FFT algorithm compute DFT of the sequence x1 of n equal to one comma 2 comma minus 1 comma 2 comma 4 comma 2 comma minus 1 comma 2. Second one, x2 of n equal to x1 of minus n. Here you have to reverse the sequence in time domain and then find DFT using DIF FFT algorithm. First part I will solve here. Second part you have to take as homework. So to compute DFT of x1 of n, we have to draw the butterfly diagram. In last class I have given the butterfly diagram to be used in computation of 8-point DFT of x of n using DIF FFT algorithm. Now to this butterfly diagram we will give the inputs. x1 of 0 is 1, x1 of 1 is 2, x1 of 2 is minus 1, x1 of 3 is 2, x1 of 4 is 4, x1 of 5 is 2, x1 of 6 is minus 1, x1 of 7 is 2. Now we will compute the outputs of first stage of this butterfly diagram. Here we are having the first stage, second stage, and here third stage. At this point we will be getting 4 plus 1 5, 5 into 1 5. At this point we get 2 plus 2 4, 4 into 1 4, and here we will get 4. And at this point we get minus 1, minus 1, minus 2. Minus 2 into 1 is minus 2. And at the fourth point here we will be getting 2 plus 2 into 1 is 4. At this point we will be getting 1 minus 4, that is minus 3. At this point we will get 2 into minus 1 minus 2. So 2 minus 2 is 0. 0 into W8 raised to 1 is also 0. And at this point here minus 1 into minus 1 plus 1. So minus 1 plus 1 is 0. Again we get here 0. Here we get 2 minus 2 0. So output here is 0. Now we will take outputs of first stage as input to the second stage and calculate outputs of the second stage. So now we will have here 5 minus 2, 3, 4 plus 4, 8, and here 5 plus 2, 7, 4 minus 4 into minus j, 0. Here at this point minus 3 plus 0, minus 3. At this point 0 plus 0, 0, minus 3 minus 0 into 1, minus 3, 0 minus 0, 0, 0 into minus j, 0. Now taking the outputs of second stage as inputs to the last stage, that is third stage, we will compute x of k values. x1 of 0 is equal to 8 plus 3, 11. 3 minus 8 is minus 5, that is x1 of 4. x1 of 2 will be 7 plus 0, 7. x1 of 6 will be 7 minus 0, 7. Minus 3 plus 0 is x1 of 1, minus 3 minus 0 is again minus 3, that is x1 of 5, minus 3 plus 0, that is minus 3, minus 3 minus 0 is also minus 3. Now we have to arrange the x1 of k values in normal order. In normal order we get x of k as 11 minus 3 7 minus 3 minus 5 minus 3 7 and minus 3. Now we will take second question. In second question we will find the IDFT, that is inverse discrete Fourier transform of x of k that we have got here using DIFFT algorithm. So right here, using DIFFT algorithm, find IDFT of x of k equal to 11 minus 3 7 minus 3 minus 5 minus 3 7 minus 3. So in finding IDFT, we will be making use of same butterfly diagram, but now the inputs will be x of k in normal order, x of n that we get will be in bit reversed order. And also one more point to be noted here is that we have to take the complex conjugate of twiddle factor used for multiplying the output of first stage, second stage and third stage. So now let us draw the butterfly diagram to obtain IDFT of x of k using DIFFT algorithm. Now here is the butterfly diagram to compute 8-point IDFT using DIFFT algorithm. In this diagram, we will be giving x of k values in normal order as input on LHS, and on the RHS we will be getting x of n as output in the bit reversed order. You can note here the last outputs of this butterfly diagram are divided by 8, where 8 is value of capital N. In this diagram, here we are having first stage, here we are having second stage, and here we are having third stage. You please also note that You please also note that. The outputs of each stage here are multiplied by complex conjugate of Tidal factor wherever necessary. Now we will write the inputs to this butterfly diagram. X of 0 is 11, X of 1 is minus 3, X of 2 is 7, X of 3 is minus 3, X of 4 is minus 5, X of 5 is minus 3, X of 6 is 7, X of 7 is minus 3. Now we will compute the outputs of first stage. At this point, output will be minus 5 plus 11, that is 6. At this point, output will be minus 3, minus 3, minus 6. At this point, 7 plus 7, 14. At this point, minus 3, minus 3, minus 6. At this point, output will be 11 plus 5, 16. At this point, output will be minus 3, minus into minus plus, minus 3 plus 3 will be 0. So here we will have 0 output. At this point, 7 minus 7 again 0. At this point, output will be minus 3 plus 3 again 0. Now using outputs of first stage as inputs to the second stage, we will compute outputs of second stage. Output at this point will be 6 plus 14, 20. Output at this point will be equal to minus 6, minus 6, minus 12. Output at this point will be 6 minus 14, minus 8. Output at this point will be minus 6 plus 6, 0. Output at this point is 0 plus 16, 16. Output at this point is equal to 0 plus 0, 0. Output here is 16 minus 0 is 16, and output here is equal to 0 0 0. Lastly, using outputs of second stage as inputs to the last stage, that is third stage, we will compute outputs of third stage. So here the gains are 1 here for all the output lines. Because W2 raised to 0 will be having on the second line in each computation. W2 raised to 0 complex conjugate will be having, that is equal to 1. So like this on each alternating lines. Next, at this point the output will be 20 minus 12, 8. At this point output will be 20 plus 12, 32. At this point minus 8. Here also minus 8. Here 16. Here also 16. 16 and 16. The outputs here are x of 0, x of 4, x of 2, x of 6, x of 1, x of 5, x of 3, x of 7. I will write these x of n values after dividing the obtained third stage outputs here by 8. 8 by 8 is 1. 32 by 8 is 4. Minus 8 by 8 is minus 1. Minus 8 by 8 is minus 1. 16 by 8 is 2. 16 by 8 is 2. 16 by 8 is 2. And 16 by 8 is 2. On the next page I will write these outputs in normal order. So x of n is equal to 1 So x of n here is equal to, actually it is x1 of n, because we have considered x1 of k, because we have considered x1 of k. 1, 2, minus 1, 2, 4, 2, minus 1, and 2. Now you can compare this output x1 of n here with the x1 of n given in the first question. That is here 1 1 2 2 -1 -1, 2 2, 4 4, 2 2, -1 -1, 2 and 2. That means our results are correct. Dear students, one more important point you have to remember here is that the number of computations, that is the number of complex additions and complex multiplications in DIFFT algorithm is same as that of DITFFT algorithm. Dear students, with completion of the two problems in today's class and this important note, we have come to the end of FFT algorithms. From next class onwards, I will be starting the next chapter, that is realization of digital systems. Today, I will stop the class here. Thank you.